Hello everybody, and happy Steel Day. This is AISC's Steel Day Live webinar, The Life of the K Factor, presented today by Charlie Carter. My name is Brent Liu. I am with AISC's Continuing Education Group, and I will be moderating today's presentation. Hopefully you noticed these slides that were being cycled through at the beginning, leading up to the beginning of today's webinar. We are registered with AIA, the American Institute of Architects, and in conjunction with that approval from AIA, we do need to let you know what the content of today's presentation is. We are letting you know about the description. In addition to that, we've been flashing up the learning objectives for today's presentation, and it is our intent to address this list of learning objectives in the webinar. I want to introduce today's speaker, Charlie Carter. Charlie is the Vice President and Chief Structural Engineer for AISC, where he has worked since 1991. He received his Bachelor and Master's of Science degrees in Architectural Engineering from Penn State University and received his PhD in Civil and Architectural Engineering from the Illinois Institute of Technology. He is a licensed structural engineer and professional engineer in Illinois. Charlie serves as the Secretary of the AISC Committee on the Code of Standard Practice and is a member of many other committees and professional associations related to the design of buildings and steel structures. Let me say this, Charlie knows steel. Thank you for being here, Charlie. Greatly appreciate you presenting today. I'm going to hand things over to you.
Okay, thank you, Brent, and thank you all for joining us today. We will take up the topic, the life of the K factor, and my neighbor, Kevin O'Connor, is an architect at SOM here in Chicago, and when he saw the email announcing this talk, he told me that it sounded like the life of pi. It was then I realized I missed an opportunity to call this the life of K. It's really such a similar storyline. I don't know how I missed it myself. I could have had some fun with it. And it's such a similar storyline, well, except for the zoo and the shipwreck and the lifeboat and the tiger. I guess it's not really that similar in the end. So we'll stick with the life of the K factor. My parents also follow AISC information, and so they knew about this presentation. And my dad's question was, what's a K? So I think it's good. Let's cover that first, just in case they're dialed in today. Here's the table of theoretical cases for K, for columns based on their idealized end conditions. It's very familiar. We have two cases with end conditions that prevent rotation and force a curvature that's shorter than the actual length. That's illustrated on this slide in red. We say KL is less than L, so K is less than 1. The next two cases both have a buckling length that equals the actual length. KL equals L, so K is 1. The next case, you'll have to shift the table up a little bit so you can see it, but the buckling length drags way down because it's a flagpole column. It's twice the actual length because a cantilever thinks it's really twice as long when it buckles, so K is 2. Now remember that because it'll come up again in a minute. And to finish, we'll slide it up. You can see the buckling length of this column is also really twice as long. And, well, that covers the idealized cases, and I'm sure at this point I've cured my father and mother's interest in K. So we'll move on to the history. And our history goes way back in time when we didn't know much. We didn't even know of a thing called K back in this era. And that didn't stop us, of course. Whoops. Ever wonder what they'll say in the future about how we did things today? Well, let's leave that for a future Steel Day seminar. We'll just concentrate on what we know today and what we didn't know when. So today, let's look at the historical developments by time period, and this slide will start in an era before the AISC specification existed. Then we'll look at the first AISC specification, which was published in 1923. Following that, we'll review some of the major developments between it and the 1963 AISC Specification. Then we'll look at some refinements that occurred after that and through the 1989 AISC Specification. We'll also spend some time looking at LRFD refinements in the years leading up to partying like it's 1999. Finally, we'll look at the 2005 and 2010 AISC specifications. By the time we're done, I'll show you the milestones and the progression that led to the development of K and the work that now lets us take it as unity, kind of the theme of this talk. To begin with, let's get some context, and I think current state-of-the-art will be good for that. We can find that in the 2005 and 2010 AISC specifications. Section C1.1 in either one of those documents says that any method that satisfies 5 needs can be used. And let's look at those 5 things. First thing it says is we have to consider flexural shear and axial deformations. These are the results of the first-order displacements of the structure. And then it says we have to consider second-order effects. These are the additional forces and moments that occur due to displacements of the structure that are induced by the loads, like those illustrated here. This happens to be a column in the side sway mode, and the illustration shows both P big delta effects, that's the additional displacements of points of intersection of members at the connections, and P little delta effects. These are due to the deformations of members between their points of intersection, the changes in curvature. The third thing that's required to be considered for stability is geometric imperfections. These come from the tolerances for initial lean and initial curvature in the AISC Code of Standard Practice. A summary illustration of those is shown here. This is figure C 7.5 from the AISC Code of Standard Practice. The envelope of tolerances for a typical column is shown at the left. What's more of interest to us in this case is in the upper right, the initial out of plumbness, and we can blow that up a little bit and see a little better that this is an illustration of the largest permitted lean of a column, which is 1 in 500. We just use that and ignore that some columns near elevators in the building facade have to meet smaller tolerances. The difference for stability purposes does not create much conservatism by just using the largest lean tolerance of columns, so that's what we do. It makes it easier. Now in the middle right of the page, you can see the initial curvature of the column illustrated. Let's blow that up as well. And you can see what the code assumes and what design is based on is an initial curvature of 1 in 1,000. In reality, ASTM A6 for W shapes, as an example, has a slightly different formulation today that results in about 1 in 950. But 1 in 1,000 is what the code is still based on. There's a little bit of an out of phase there between what was updated in A6 and what's in the code. That'll be fixed over time. Next, it requires that we look at stiffness reductions due to inelasticity. Said a little more simply, this is that we have to consider residual stresses. Here's a typical distribution. For a W shape, the tension areas are shown in red, and they get locked in as the shape cools because the extremity of the cross-section cools first as that shape is being made. They balance the tension with their residual compression in those other regions shown in blue. Of course, the rolling changes the distribution, straightening changes the distribution a little bit, but this is a good measure of the distribution. We can also look here at how the size of the shape, the size of the cross-sectional elements can cause variations in the magnitude of and distribution of the residual stresses. You can also see in the lower right there is a change for the a different pattern for welded shapes. And the fifth thing that's required to consider variability is the fifth thing that's required is to consider variability in component and system stiffness. These are things like material and cross-sectional variations, and they are accounted for in the resistance factor for LRFD or the safety factor for ASD. So these are the 5 things, and I call them 5 things. Please remember that technical term. It'll come up again later. Note that these 5 things affect both the analysis results and the member strength equations. It is not just one or the other, it's both. Now the whole picture for how analysis and member strength equations work together in stability design is covered in the specification. It's also covered in greater detail in this document, AISC Design Guide 28, which will be available in December. Larry Griffiths of Walter P. Moore and Don White of Georgia Tech are the authors, and I want to give them an additional credit here, not just for the design guide. Larry and Don wrote a chapter on history that was not used in that design guide, but it was hereby saved from the cutting room floor because much of what they wrote is captured in what I'm presenting in the lecture here today. So they are, without knowing it, my co-authors. So that's enough preamble. Let's dive into the history. And I said before, we'll start out before the AISC specification existed. And by before, I actually mean way before. We'll start in 1729, to be exact. That's when von Musschenbroek published the first paper concerning the strength of columns. I think it is it to the right. The image that you see at the lower right, you can go on Google Books, as I did. I think that's the paper in which this was published. If you go on Google Books and search for this, please read it and let me know if I'm right. I'm afraid my Latin is just a little rusty, and so I couldn't tell for sure. But this is, in fact, the only von Musschenbroek reference from 1729 that's on Google Books. In any case, von Musschenbroek gave this empirical column curve in which P is the column strength, B and D are the column width and depth respectively, and L is the column length. K was stated as an empirical factor. We have to give von Musschenbroek some credit. It has a K factor in it. It's lowercase and it's not in the right place, so if he was thinking of RK, I guess we'll have to say nobody's perfect. We can move forward to 1759. That was when Euler gave his equation, which he determined for a column with one end fixed and the other free, a flagpole column. I told you that would come up again. P is the buckling strength, L is the column length, and the constant C is what Euler called the absolute elasticity. And you can see that Euler also had a K in the equation, but you have to know it to see it. I told you the K for this column that he was testing as a cantilever was 2. So if you take 2L and square it, KL squared is equal to 4L. So there we have a K in his equation, even though it wasn't K yet. Engesser proposed the tangent modulus theory in 1889. This was a modification that produced an upper bound on the Euler buckling theory. It started to reflect what we now know are residual stresses. He revised that theory in 1895 with a reduced modulus theory. This was more of a lower bound on the prediction of the column buckling strength. Along came, this was used as the correct column buckling theory until 1947 when Shanley published the tangent modulus buckling formula, and the tangent modulus was intermediate between the tangent modulus and the reduced modulus theory. I imagine that the ghostly apparitions of von Musschenbroek and Euler implored in unison, but what about this thing we do not yet know to call capital K? Okay, wait, we're getting ahead of ourselves. I said this was before AISC in the timeline, so now I have to back up. But it was important to get Shanley's contribution in while we were talking here. It's also important that we talk about those 5 things, which of them are being addressed and which are not. And I guess it is no surprise at this point that the work to date does very little to address the 5 things. The 5 things are things we know today. They knew very little of these things back then. The practices of the day tended to compensate, however. Heavy masonry infill was very common in buildings, as was the presence of uncalculated strength and stiffness. The analysis methods of the era were conservative by nature, and although the term skyscraper had come into existence, it described buildings like the home insurance building shown here. They were on the order of only 10 stories tall. In 1923, AISC published the work upon which 5 eminent engineers collaborated. It's called the Specification of the American Institute of Steel Construction for the Design, Fabrication, and Erection of Structural Steel for Buildings. Their deliberations resulted in 9 whole pages of text. That was less than 2 pages each. Amazing that it could be covered in that little. But the document that they produced was proposed for acceptance. It was not yet a standard. It was proposed for acceptance by the engineering community and steel construction industry. Of course, we know today that this document was accepted. It became the cornerstone upon which all else since has been built, and that we know that these were some of the giants on whose shoulders we stand today. The allowable stress for column buckling was given as shown in this curve. F sub A is the allowable stress, and it's plotted as a function of L over R, where L is the unsupported length of the column and R is the corresponding least radius of gyration of the section. And if we put some numbers and equations on this curve, the curve had a 15,000 psi allowable plateau. That was good for values up to L over R equal to 60. And the parabolic function shown here controlled thereafter. Now, in the era of this type of curve, consideration of the combination of stresses was required, but the basis of the requirement was fairly crude. It simply said, members subject to both direct and bending stresses shall be so proportioned that the greatest combined stress shall not exceed the allowed limits. In this era, we have essentially the same story on all the 5 things as we had before. Very few were addressed, but for most buildings, all of the implicit compensating factors continued to exist as well. There were, however, notable and important exceptions. Landmark structures like the Empire State Building, Manhattan Tower, and Chrysler Building approached and exceeded 1,000 feet in height, and they did this without any clear understanding of system buckling, secondary effects in frames, and effective length factors. Certainly those compensating factors were now beginning to be tested by these designs. After 1923, we'll move into the next era, and there were several revisions of the AISC specification that ensued. This period was a time of growth in both knowledge and application, but treatment of stability evolved at a much slower pace. Let's look at how, and we'll start to do that with the 1936 AISC specification. The allowable stress for column buckling was given as shown in this curve. It's fairly similar to what we saw before. If you have a good eye, you'll see that the blue portion of the curve to the right is identical to the blue portion of that curve, or to that portion of the blue curve I showed before. But in this comparison, you can see the difference. These are graphed together, and you can see the change that was made in purple. Instead of going out to 60, value of 120 was now the change, the point of change between inelastic buckling and elastic buckling. And you can also see the different column curve that was selected. We're doing a little better in this range in terms of strength. And we're also starting to look a little more like what we look at today in terms of our column curves. Moving forward, considerable research was undertaken in the late 1940s and 1950s. This research broke ground on things like residual stresses and other factors. Those factors included initial out of straightness, the eccentricity of the load, the end fixity, transverse loads, and the effect of local and lateral buckling on column strength. The Column Research Council, which is now known as the Structural Stability Research Council, or SSRC, published column strength curves. And these curves and their refinements are still what we use as the basis for many code provisions today. column buckling provisions were based upon the Johnston parabola in the inelastic range until it merged with the Euler curve for elastic strength. Members subject to both axial and bending stresses were proportioned by an interaction equation, but it reflected simple combination of stresses. There was a 1961 AISC specification. It has the distinction of being the only AISC specification that was not written into an AISC steel construction manual. This was in spite of many landmark improvements that were made in it. In fact, you can see the start of the modern formulation of inelastic buckling here from that specification. Note also that Fy was now a variable in the equation. This is the era in which it began that multiple grades of steel could be chosen. There was now a variable ASD factor of safety. They didn't call it ASD back then. They didn't know there would be an LRFD yet. And also C sub C, a familiar divider between inelastic and elastic buckling, came into being. And Euler's in there, but just a little hidden in the form of constants. This plot illustrates the comparison between all of these years that I've covered. You can see for 33 KSI steel, which is fairly similar to what we would have been designing earlier, we're doing a little better in the inelastic range. In the elastic buckling range, we're lower than previous predictions. That's primarily due to the variable factor of safety. Although the concept of effective length was discussed in the commentary, you can still see L over R. It wasn't until the 1963 AISC specification. That's when K, the effective length, KL, became explicit in the AISC specification. So at this point, we should take a moment and we should say happy birthday, K. According to this timeline, I'm not sure which it is. It's either 234 years old or a newborn. And it's hard to tell which is the correct answer. But let's call it a newborn. It was new in 1963. The alignment charts were first published. They were published by Kavanaugh in 1962. If you're going to have a K, you need something like this. This image shows the sway frame case. There was a similar chart for non-sway frames, also published at this time. These charts were first introduced from unpublished notes in 1959 as the Julian and Lawrence charts. They were published originally for incorporation into the Boston Building Code, and then they made the AISC specification. So here K has finally appeared in the equation for the inelastic buckling range. A similar variable factor of safety, but now with K in the formulation, existed. And C sub C was used as in 1961. In the elastic range, this was the formula. Again, very similar, just modified with K. Treatment of interaction was improved in this era. At low levels of axial stress, the addition was still linear. At higher levels of axial stress, however, an amplification factor was introduced to reflect that lateral displacements generate a secondary moment that must be accounted for in the member bending stress. So for the first time, side sway stability was to some extent explicit in the AISC specification. Many of you will recognize the ratio that's circled here as the B1 factor that accounts for P little delta effects in more modern versions of the AISC specification. P big delta or B2 effects were not explicit though, but we're really starting to see some things now. What about those 5 things? Well, there was substantial growth in knowledge in this era and much more explicit consideration of those stability effects in the specification, as well as in design office practices on the design side of the equations. On the analysis side of the equations, however, this remained to be developed. Now, if you have an astute memory of all those assumptions that go behind K, many times we forget those were there because it's what we learned when we started talking about K and when we just went on and used it. But if you have an astute memory of all those assumptions that go into making those alignment charts, you probably should be asking the question, was K okay? Well, it's fair to say that K was used, but it was introduced not without compromise. It was true then, and it remains true today, that few, if any, of the assumptions that are behind those alignment charts are actually satisfied in real structures. In the end, we can say that K was accepted because it did something, and that was better than doing nothing. This era also marked the beginning of changes in the way buildings were designed and constructed. Building systems were evolving and architecture was changing the way structures were configured. More changes were to follow. Moving past 1963 into the era of AISD refinements, there were 3 more revisions of the AISC specification in its ASD form. These were made in 1969, 1978, and 1989. None of these revisions made any substantive changes to the column buckling equations or the interaction equations, but some other refinements were made, so let's look at them. In 1969, the word stability was explicit for the first time in the requirement that general stability shall be provided for the structure as a whole and for each compression element. Also, attention was now given to overall frame behavior as opposed to member behavior. The commentary was improved to help in the determination of the effective length factor, K, which needed that help because of all those assumptions. In 1978, the commentary guided structural analysis and determination of secondary effects on frames. For the first time, the term P delta was used and second-order analysis methods were discussed. Now in 1989, little was different except for a basic reorganization to match the format of a newer alternative method called LRFD that had been introduced in 1986. Significant advancements in stability analysis and design requirements had been made in the 1986 LRFD specification, but these were not added when the 1989 ASD specification was written. This may have contributed to a mistaken perception at the time that stability was an LRFD concern, not an ASD concern. Now, in spite of the advancements noted above, stability considerations in design office practice largely remained limited. At the time, the heights of skyscrapers reached the pinnacle of the century. Every system used in building architecture, structure, and mechanics was being developed and innovated. The curtain wall and open floor plan with longer and longer spans dominated. Even the marketplace was changing. Construction management split as a discipline away from the role of the architect, and CM influence would further drive the lightness and flexibility of structural systems. Economic evaluations dictated that framing would be economized by more exact designs and limited use of lateral framing. The more advanced projects like the Sears Tower, John Hancock Tower, and Standard Oil Building, shown poking through the clouds here in Chicago, received significant attention to stability effects. Nonetheless, building systems were changing, and this impact would manifest itself in many ways, including a heightened need for more advanced stability analysis and design requirements. The John Hancock Tower in Boston is perhaps the most notable example of a building with design and construction aspects that outpaced the technology of the code in the area of stability, a project that was ultimately beset with a number of different structural issues. Stability was cited as the reason that many panels in its all-glass facade popped out. Other examples exist, but none are as dramatic in their illustration of the need for further development of provisions to address stability in the design of buildings at this time. Then there was LRFD. AISC and SSRC, and there were others, were advancing the state of the art, and this was reflected in the first LRFD specification in 1986, as I mentioned before. In the inelastic range, a new column curve was introduced. In the elastic range, the formulation was still based upon Euler buckling, but it may have been hard for some to tell due to the use of lambda sub c as a variable to divide inelastic and elastic buckling instead of KL over R or C sub c. It was easier to see Euler in the formulation of lambda sub c, but not automatic. Second-order effects were included in the calculation of axial forces and moments. This greatly simplified the resulting interaction equations. And what's shown here is the LRFD interaction equation for high axial force ratios. And this one shows the equation for low axial force ratios. There are some other significant developments at this time. Frame behavior was explicitly addressed. Frame stability was recognized as a system buckling phenomenon. And it was required that second-order p-delta effects be considered in the design of frames. Structural analysis was required to include axial deformations, and the effects of frame instability was evaluated under ultimate loads. An approximate second-order analysis procedure called the B1, B2 method also was added. In 1993, the LRFD specification also had some developments. Stability treatment was expanded to both braced and unbraced frames. Leaning columns were recognized for the first time. Emphasis was added on acceptable methods to calculate the effective length factor K, including the effects of those leaning columns on different versions of the K-factor equations. There were not many changes in the 1999 LRFD specification relating to stability. There were some stability items added, including bracing strength and stiffness requirements that were added. But all along in LRFD, this was LRFD. And these advancements were largely lost to the engineering community that still used ASD as the predominant method of design. ASD, however, was fallow as all new developments were being made in LRFD. Yet the same advancements would have been written into ASD if LRFD had never come to exist. Now, we've got a lot to follow this, but Brent would like to take a break here and do a quick polling question. I think he wants to see if you're still paying attention. You can take it, Brent.
Thank you, Charlie. Yeah, we do have a couple polling questions here we'd like you to participate in. And as Charlie said, we want to see if you're paying attention, but we also look at it as an opportunity to make our presentation more interactive today. So you're going to have a question pop up on your screen here. Choose the appropriate answer and hit submit, and we'll see how everyone's doing with today's lecture. So here's the first question. In what specification did the K-factor actually appear in the column buckling formula? Was it 1961, 1963, 1986, or in 2005? Again, in what specification did the K-factor actually appear in the column buckling formula? Give you a moment to get your answers submitted. A couple of you have sent them through the chat. Go ahead and use the polling option to send that answer in. All right. And looks like most of you have submitted, so I'm going to let this roll. And as you can see the results, the correct answer is 1963, and most of you chose 1963. Very good. All right. Our next question. Charlie talked about the original specification being written by 5 engineers. The question is, how many can you name? 0, 1, 2, 3, or 5? The original specification was written by 5 engineers. How many yourself can you name? And it looks like most of you are being honest, and they're saying 0. Charlie, I put the question back to you. How many can you name, Charlie?
Well, I can cheat because I have the original specification sitting in our library, and so to be fair, I wouldn't expect you to know many of these because we didn't even cover it in the lecture. But it's interesting to look back and learn that the 5 original writers who created less than 2 pages each were George Swain, Milo Ketchum, E.R. Graham, W.J. Thomas, and Wilbur Watson. Certainly titans of their time. So now, do I take it back, Brent?
I'll go ahead and take it back. We left off on slide 98. There you go.
Okay, and thanks for those polling questions, Brent. Felt like a little bit of like Ask the Audience. I like that as a break. But let's get back into it. We're now up to today. This is a good time. We can say thank goodness there was a solution to ASD going in one direction and LRFD going in another. That solution was the 2005 AISC specification that resolved the duality. It unified previously separate ASD and LRFD methods, and we think we did that using the best of both. This showed well in the column equations. Gone was lambda sub c. In its place was a familiarity of terms like KL over R and F sub E. In addition to the formulation with phi, and a higher phi at that, due to improvements in column curves and materials, there also was an ASD formulation that used the exact same equation, just divided by a factor of safety. Euler buckling looked like Euler buckling again, as did the LRFD and ASD formulations in the elastic range. Interaction checks were based on the LRFD formulation, so they remained essentially unchanged. They were generalized, though, to also address ASD, one set of equations that would address both methods. Now, that's just on the calculation side. The real leap forward in 2005, carried forward into 2010, was to address stability properly on both the demand side and the analysis results and the strength side in the member strength equations. This had never happened before to the extent it did in 2005. In 2005, it was permitted to use any approach that satisfied the 5 things. You do not have to use one of the methods that's listed in Chapter C or Appendix 7 to assess the stability of your structure, but we do provide the methods that are shown here. We didn't want to leave you on your own in all respects. So 3 prescriptive approaches were provided: the direct analysis method, the effective length method, and the first order analysis method. The direct analysis method was new in 2005, completely new. The effective length method remained similar to the traditional approach. It had been named the effective length method at this time, but it had been modified slightly, limitations put on it. And in addition, the first order analysis method was new in 2005. It was put in as a way to do first order analysis, but still satisfy the requirements of the AISC specification that require second order analysis. And how do you do that? Well, you go to the direct analysis method. You add the assumptions that are necessary to get a conservative method that is easier to apply. And that resulted in the first order analysis method. But it's derived from direct analysis. These methods are also addressed in the 2010 AISC specification with simplifications, refinements, and clarifications based upon usage since the 2005 specification was published. Each of these methods is further illustrated in the information that was provided in the handout that you got. There is the paper form of this presentation that goes through the things I'm saying today. There's also an appendix or an attachment A to that handout, which is a paper from the AISC Engineering Journal that I wrote with Lou Geschwinder to run through each of these methods on some fairly academic frames, but we produced some useful design examples. Even though the frames are academic, the use of the methods is illustrated, and we think it's very practical if you're going to try out one of these methods and see how it's done. All 3 of these methods are also covered in AISC Design Guide 28. I told you about that earlier, and I'll remind you that'll be on the website in December. Now, we won't get into the gory details on these methods here and now, and I'll just ask you to hold your applause that we won't do that, please. But let's actually look at direct analysis, because this talk, after all, is about the life of K, and that is the way that today we can sign with K equals 1 and see the life of K come full circle. Let's do that by discussing how direct analysis works. First, it requires a direct second-order analysis, or you can do a first-order analysis and then add the second-order effects with a B1, B2 amplification. The second thing it requires is that we have to model the frames with notional lateral loads. Remember that 1 in 500 column lean, 1 over 500 is 0.002. And so we take the vertical load, we multiply by 0.002, and we put a fictitious lateral force. You can put it at each floor level, you can put it at each column node, you can do it however you want, but you can put notional lateral loads, and what that does is it accounts for the initial lean of the columns. Third, we have to reduce the stiffnesses. We use reduced stiffnesses EA star and EI star in the analysis. And this is the whole idea of direct analysis. With a K-factor, we're trying to adjust the length of the column to a value that gets us a safe design, overestimating the length in a moment frame. In the direct analysis method, we're going to try to overestimate the actual forces and leave the length unchanged. And so that's the whole key. You have to soften the structure to get the right force distribution. That's what EA star and EI star do. It's the magic. There's really, in the end, I call it magic. There's no magic involved. It's just a way to get an answer that produces a safe result. Usually EA star and EI star are going to be equal to 0.8 times EA and EI respectively. There's also a factor tau sub b that's often 1, but it might not be. You should look at it. And there's also a way to eliminate calculation of tau sub b in the actual provisions. The fourth thing that we have to do is we have to use strength level load combinations. That's LRFD load combinations, which is easy if you're doing LRFD. If you're choosing to do ASD, all is not lost, however. You just multiply your load combinations by 1.6. That factors them up. You get your results. You divide the results, the resulting moments and forces by 1.6 for design. And what that is, you need the strength level drift of the structure to get the right amplification for second order effects. You can't do it at the working stress level. You have to do it at the strength level. And let me talk about one alternative. I said you have to put notional loads on. You don't actually have to put notional loads on. You can model the out-of-plumb geometry if you prefer. Now that's good for an existing building, not very practical for a new design that isn't built. You don't know where it's going to be. But if you know the actual geometry, you can model it. And this is an effective way to go about the analysis. You can eliminate the notional loads at that point and perhaps simplify things. And in the end, that's it. By softening the frame and increasing the drift, we get the forces and moments that can be used in design with K equals 1. So that's pretty simple, right? It will not surprise you to find out that all 5 things are explicitly addressed in this method. Those 5 things are things we know now need to be addressed, and certainly if we provide a method in the AISC specification, it has to satisfy those things. Now I'll point out that effective length method and first order analysis method also satisfy the 5 things. They do so in a combination of explicit ways and implicit ways, but those 2 methods are deemed to comply with the 5 things that are required by the committee that wrote these 3 methods and the stability requirements in general. So how are the 5 things addressed? Let's just run through that for completeness. Well, member, component, and connection deformations are addressed directly in the analysis. Second order effects, both P delta and P big delta and P little delta, are addressed directly in the analysis, either by doing a rigorous second order analysis or the first order analysis with a B1, B2 amplification to add the second order effects. Whoops, I got ahead of myself. Structural out-of-plumbness is addressed with the use of notional loads. Alternatively, you can do it with direct modeling of the out-of-plumb structure. And member out-of-straightness is accounted for in the column design equations for its effect on member strength and in the use of the reduced stiffness for its effect on the structure stiffness. Finally, residual stresses are accounted for in the column design equations for their effect on member strength and in the use of a reduced stiffness for their effect on the structure stiffness. And now finally, variability in component and system stiffness is accounted for in the resistance and safety factors for their effect on member strength, and then also in the use of reduced stiffness for its effect on the structure stiffness. So you can see that these 5 things are addressed, some of them on one side of the equation, some of them on the other, and some on both. But in the end, the 5 things are addressed through a combination of modifications to the analysis and modifications to the design strength equations. So I think direct analysis is logical and straightforward. If you haven't already, give it a look. There's some pretty good guidance available on it. And but I don't want to talk about direct analysis as we end. We were talking about our good old friend K, and so as we wrap up, let's go back to that. As we do, you can kind of see this talk is about the alpha and the omega. We started at the beginning of K when we didn't even know what K was, and now you can see a means by which it can simply be set equal to 1 in our designs. And I again credit Larry Griffiths and Don White for the work that they did that I used in the preparation of this lecture. I'll also give some credit to an old friend, this man of steel, Bob Disquay, who actually gave me the idea for this talk. When we were finishing the direct analysis method, Bob commented to me that he had, as a much younger man, the Alpha Bob, started his career at a time before there was a K factor. And he lived the difficult task as AISC Chief Engineer of introducing it to the engineering profession. He added that the profession at the time was not initially receptive to the concept, and it was resisted as unnecessary. I hadn't needed it before, why do I need it now? Of course, you know that the Bob on the left, as he became the Bob on the right, was successful in promulgating K. But it is a surprise to some today that we used to design without it. And now Bob says he has lived to see the need for K that he convinced so many people of eliminated. His one-word summary was remarkable, and I think he's right. With that, I thank you for your attention, and I'll give it back to Brent, and he's going to bring us through the end of the presentation.
Okay, thank you, Charlie. We do have one more polling question, and then we're going to answer a few questions from the audience that have come through today. Here's our next polling question. In the direct analysis method, how is structural out-of-plumbness addressed? Is it A, use of notional loads, B, direct modeling, C, applying a phi factor or omega factor depending on LRFD versus ASD, or D, A or B is acceptable? Again, this is in reference to the direct analysis method. How is structural out-of-plumbness addressed? Use of notional loads, direct modeling, applying a phi or omega factor, or D, A or B is acceptable? Results are rolling in, and we'll show how everyone is viewing that question. Most of you have answered D, and that is the correct answer. Both of those options are an acceptable way to address out-of-plumbness. All right, we do have time to answer some questions that have come through, Charlie, and so I want to ask you a few of those. You mentioned an EJ paper that has examples that compares the 3 methods of stability. Can you clarify again what that paper is?
Yes, the paper actually is in the handout that you downloaded or could have downloaded for this lecture. However, if you did not, I can tell you the issue of Engineering Journal. It's a paper called A Comparison of Frame Stability Analysis Methods in AISC 360.05, and it's in the third quarter 2008 Engineering Journal. It was authored by Charlie Carter and Lou Geschwinder. It was a fun paper to work through, and I hope you find it useful.
Okay, thank you. Next question. For ASD, why do we need to be if you use ASD for the direct analysis method, why does it need to be multiplied by 1.6 to normalize to an LRFD combo when the ratio of LRFD to ASD is actually 1.5?
Well, that's a good question. A very good question, and it's received a lot of debate within the AISC Committee on Specifications. And if you think about second-order effects, they're not linear. If the calculation was linear, that same relationship between ASD and LRFD would hold, and it could be 1.5. But at the deformations that we get to, the studies that the Task Committee on Stability has done suggest that a factor higher than 1.5 is used, and so they chose 1.6. Just reflects the nonlinear nature of those deformations. When you're pushing the structure beyond the working stress level to the ultimate level, you don't get a linear variation in the deformations. Great question.
Okay. Question along the lines of notional loads. Again, based on the polling question, the notional loads are used to account for out-of-plumbness. But one question that has come in is, are notional loads applied laterally, globally, or locally to a member? For example, if the member is not vertical, are the notional loads applied normal to that member?
Yeah, that's also a good question. A lot of structures you may want to apply it throughout the structure, not globally. If you have a building that's a nice regular system of floors and frames, it's easy to put them at the edge, run them through the diaphragm, and just load the frame. But if you don't have that, you probably want to distribute it throughout. And maybe the software that you use is set up to do that anyway. But the crazier the frame gets, the more you're going to have to consider just putting the lateral force at each node. You take the load in the column, you multiply by 0.002, and you put that laterally and run the analysis. If you have a diaphragm, you can lump it all together, and it doesn't make any difference unless you're designing the diaphragm. Now remember, these are just fictitious forces. They're only used to get the right forces in the lateral frame. You have to take them out at the foundation. You don't design the foundations for them. So the way to do that is you put equal and opposite forces at the foundations. You wouldn't want to take it outside the lateral frame.
Okay. And then someone has asked how the notional load, how was that calibrated? How do we come up with that number to use for the notional load?
Well, the notional load, the 0.002, literally is just a 1 in 500 column lean that's permitted in the AISC Code of Standard Practice. We know that columns are going to be at that or less for acceptability in the tolerances in the Code of Standard Practice. I should point out, you're permitted in the specification if you know what the lean of columns is. If your building is being erected and you have a field survey that says this is the initial position of the structure, and something has changed and you want to go back, you can now model with the actual lean. You don't have to do the imperfect geometry in your model. You could adjust your notional loads to 0.001 times. If you know that that's there, you can use it. If you don't know it, you just use the 0.002 because that's the maximum permitted. But it's all based on the 1 in 500 lean in the permitted lean in the columns based on the Code of Standard Practice.
Okay. Here's a question regarding the direct analysis method. What type of structure / analysis cannot be applied with the direct analysis method?
Well, the direct analysis method is unlimited. You can use it for anything. It's probably most suited for moment frames where you get to reduce the stiffness, add some loads, call K equals 1, and have an easier design. In braced frames, you can already say K equals 1, so there may not be as much advantage there. There's definitely an advantage if you're starting to mix systems, braced frames and moment frames together. It's hard to know what really is happening with K in those cases. Another real good case for direct analysis is where you have a structure that does not have a nice regular arrangement of floors and columns. Industrial structures, power, nuclear type structures, you can find some things that columns have different lengths. The framing changes because we have process piping or some other thing going on that we can't put bracing in this area. We're changing the structure to accommodate. That's where direct analysis really shines. But it's unlimited. You can use it anywhere. Effective length method, first order analysis method are both limited to structures that have calculated B2 less than or equal to 1.5. That's a pretty permissive limit. You're saying your second order effects are 50% of your initial effects. That's pretty high second order effects. Most structures don't get that high, but those are the limits placed on those methods. That doesn't mean you couldn't calculate a K with a B2 value higher. It just means you'd have to be a lot more careful if you did it. We limit the method as we've prescribed it so that you can't exceed 1.5, at least as far as how we've prescribed it.
Okay. Here's a question for you. Again, the direct analysis method. How are connection deformations addressed in the direct analysis method?
Well, the direct analysis method does not tell you how to address connection deformations. If you're using rigid connections, the conventional assumption is that they maintain the angle. I would think you'd have to do more if you're trying to do something like a partially restrained moment connection. You would have to do more. You'd have to know the initial loading curve and then the curve after shakedown, and you'd have to address it with that. The direct analysis method doesn't tell you how to do that. It just says you have to address that if you're going to do it. Probably that's why most people don't design with PR connections. There are ways to do that are simplifications. The old type 2 with wind approach is probably the most well-known simplification. But the typical design probably goes to the fixed end connection where we permit the assumption that the angle is unchanged, even though we know it isn't quite unchanged.
Okay. Along the lines of K equaling 1, a question has come up, is it still acceptable to design with a K greater than 1, as has been done previously?
Yes, yeah, that essentially you would be using the effective length method, and that's a permitted method. There's nothing wrong with the effective length method within the limitations that are provided in the AISC specification. There are methods. You have to account for things. Leaning columns are common. They increase the K. Take a look at how we address that in the paper that I mentioned earlier, the engineering journal paper. That was one of the things we wanted to highlight, especially because it's such a common thing in today's frames where the actual moment-connected portions are limited. And it can have a big effect. We did one example with two columns, one leaning on the other, And we did another example with 4 columns, 2 of which leaned on the other 2. And you can get a real feel for the difference, how it affects the K-factor. You can see it right in the paper because we did it all by hand, in the equations right in front of you. Nothing's buried in computer analysis, let's put it that way. But yeah, you can have K greater than 1 if you're doing the effective length method. I'd expect you to have that for a moment frame.
And again, just to emphasize, that paper was included as a download for today's presentation.
Right, it was actually in the handout. It wasn't a separate download. It's the last half of what you downloaded for the presentation materials.
Correct, yes. Here's a question about notional loads. Why are notional loads important when they are so much smaller than the lateral loads from earthquake and wind forces?
Well, that's a really good question. You have to think, when are the notional loads important? They're much more important in the gravity load cases. And really that's where we're getting, where you have the large vertical load, that's where you're producing the most destabilizing effect on a structure. A lot of structures are not sensitive to stability effects, but if you have a structure that is sensitive, it's important in those gravity load cases to reflect the notional loads. Once you start looking at earthquake and wind loads, yeah, the notional loads for 0.002 times the gravity loads in a typical building are going to be quite small. But they may make a difference for you in those gravity load cases, and that's where I think you're going to find that they do make a difference.
Okay. This question here is, can you use a direct analysis method, or would you use the direct analysis method to evaluate the serviceability of a structure if you had no load factor on there?
Well, direct analysis and serviceability don't go together. Serviceability is something that you're checking probably for serviceability load combinations, not the strength load combinations that we would use for design of the structure. Well, if you do check your serviceability for the strength load combinations, and you meet limits that are intended for serviceability, you're doing more than you need to do. So direct analysis, we're softening the structure so that it drifts more to get the right forces and moments for design. I don't want to soften the structure with direct analysis to check my serviceability limits. So I think you have to keep those separate. Direct analysis really doesn't help you for, say, drift checks, or the loads from that aren't going to help you with your deflection checks. You've got to go back to the serviceability load combinations. Those aren't, I'll add, by the way, those aren't ASD load combinations. Serviceability load combinations are different than ASD strength load combinations.
Okay. We're getting close to needing to wrap things up. We're running over time as it is. One question that keeps popping up is, can I get a download of today's slides? Just to be clear, we have provided a handout that includes a couple papers that support today's presentation, which this is based on. Additionally, we are providing the recording of this webinar. It'll be released next week. You certainly can go back and watch that at any time for additional reference, but we have not provided the slides for today's presentation as a handout. So, thank you, Charlie. Greatly appreciate your presentation today. I want to thank all of you that have joined us. There are several questions that we were not able to get to, and together with Charlie and the Steel Solutions Center, we'll work to answer those questions. If you're not familiar, AISC has a Steel Solutions Center. You can submit your questions to them anytime, not just at a webinar, but anytime, and get feedback on your questions that pertain to the design of structural steel.